Today on Let's Talk Chemistry, we're going to be talking about electron structure in atoms.
So, to understand electronic structure, we first need to talk about light. Now, visible light, radio waves, and X-rays are all types of electromagnetic radiation which carries energy. All the types of radiation travel through a vacuum at a certain speed called light speed. They all have a wavelength and a frequency, which is the number of wavelengths that pass through a given point in 1 second. And these two things, the wavelength and frequency, are inversely related. Frequency is expressed in hertz, and wavelength is expressed in these common units. So now we're going to talk about some people who made important discoveries to our current understanding of light and electronic configuration. So the first person we're going to talk about is Planck, who was a physicist in about the 1600s. He said that energy could be absorbed or emitted in chunks called quantums, and the energy of a quantum is the frequency times Planck's constant. In 1905, Einstein expanded on this theory when he said that light travels in packets called photons, and that the energy of these photons was Planck's constant times the frequency of the light. In 1913, Niels Bohr used these two theories to explain the line spectra. When radiation is split into wavelength components, a spectra is produced for a range of colors, and it was found that certain gases under reduced pressure with a high voltage passed through them emitted a specific color. And this color, when it was passed through a prism, created specific colors in the spectra, but not all of them, which is called the line spectra. This spectra was first discovered through the use of hydrogen and became the basis for Bohr's model. So to explain this, Bohr assumed that electrons moved in a circular pattern around the nucleus and came up with three postulates. One, that only orbits of certain radii, corresponding to certain definite energies, are permitted for the electron. Two, an electron in a permitted orbit has a specific energy. And three, energy is emitted or absorbed as a photon by the electron as it goes from one energy state to another. Bohr then calculated the energies of each orbital, then said that electrons jump from one energy state to another by emitting or absorbing photons with energy levels corresponding to the difference between the energy levels in the orbitals. He then said that the existence of these spectral lines was because of the quantized jumps of the electrons from different energy levels. However, this theory only works with hydrogen, so it is incorrect, but it did lead us to our common theory that we use today. After that, Louis de Broglie suggested that electrons have a wavelength characteristic found with this equation, and this was later found to apply to all matter. Next, German physicist Heisenberg created the uncertainty principle, which says that we cannot know the exact momentum and location of an electron in an atom at the same time. Finally, in 1926, Austrian physicist Schrödinger created the model quantum mechanics for describing and talking about subatomic particles, and this is the same model that we currently use today. This model uses orbitals, which describes the specific distribution of electron densities, or where the electrons are most likely going to be at, to describe electron location in an atom. And these orbitals therefore have a specific energy and shape. So this model uses three quantum numbers to describe each orbital. The first number it uses is the principal quantum number, or n. As it increases, the orbital becomes larger, and the electrons spend more time farther from the nucleus. The second number, the azimuthal quantum number, L, can value from 0 to n-1, and it defines the orbital shape. The third number, the magnetic quantum number, or m subscript L, can value from -L to L, and it describes the orbital orientation in space. So now we need a way to represent these orbitals. The 1s orbital is represented with a sphere, and this sphere shows where the electrons are most likely to reside. For s orbitals, as n increases, the size of the sphere increases, and so does the distance from the nucleus that we're most likely to find electrons. For p orbitals, the region where we're most likely to find electrons is dumbbell-shaped, and starting at n equals 2, for each shell, there are 3 p orbitals, and each p orbital has a different orientation in space. Like s orbitals, p orbitals increase in size as the principal quantum number increases. When n is 3 or greater, we get 5 d orbitals, which vary in shape and orientation as shown here. Once we get to n equals 4 and on, there are 7 f orbitals. The energies of these orbitals increase with n, So the 3p orbital has more energy than a 2p orbital would. However, all three 3p orbitals have the same energy. Now, the electrons populate these orbitals in specific ways. Two Dutch physicists discovered that there was actually a fourth quantum number, the quantum spin number, when they postulated that electrons spin in two different directions on an axis. And this fourth quantum number is denoted by m subscript s. Austrian physicist Pauli then used this discovery to create the Pauli exclusion principle, which governs the way electrons are arranged in atoms. This principle says that no two electrons can share the same four quantum numbers in one atom. So this led to the idea that an orbital can have a maximum of 2 electrons and that they must have different spin directions. So now that we've discussed this, we're going to move on to the topic of electron configuration. Because electrons always try to be in the lowest possible energy states, or ground states, we fill the orbitals in order of increasing energy. So the 1s orbitals are filled first, and then the 2s orbitals and 2p orbitals, and so on. We can represent these electrons configurations by writing the symbol for the occupied subshell, followed by a superscript number indicating the amount of electrons in that subshell. We can also use an orbital diagram as shown here, which shows electron spin and whether the electrons are paired or unpaired. Now, Hund's rule is the final piece to the electron structure puzzle. It states that electrons will occupy orbitals singly to the maximum extent possible. An example of this would be that in the 3 2p orbitals, electrons will occupy each orbital singly first before another electron is added and made into a pair. So in order to write electron configurations in a simpler manner and one that takes up less space, we use abbreviations. At the end of every period in the periodic table, a shell is filled. So when we go to start the next period, if we want to write the electron configuration for that element, we start with the name of the element that completed or filled the last shell, followed by the next subshell in the current shell. For example, the electron configuration of potassium is commonly written as argon 4s1. So this pattern is basically followed for all the rest of the elements, and the periodic table shown here will give you the electron configuration of all of the elements. There are, however, a few electron configurations that don't seem to fill in a predicted manner, like chromium. This is simply because of the closeness of the 3d and 4s orbital energies. And that's about it for electron structure of atoms.